Good day, students. This is General Science 101. I'm Professor Safyan, and we are going to take you on further from what we discussed in the last lessons. Going back to the last lesson, we discussed the differences between science and humanities, which says science is something which deals with experimentation, has a certain method, a certain procedure. We looked at the essence of the scientific method. In the essence of the scientific method, we said you observe something, on the basis of that observation, you form a hypothesis, you put the hypothesis to a test in an experiment, and on the basis of the experiment, you verify whether the hypothesis is true or not true. If it is true, you report it. If it is not true, then of course you rethink your hypothesis and make another line. Yes, of course, we did discuss in that portion that in this process you also add, in the modern world, something you do research on to see whether someone else has done some work on it and what that person or that team has done, and then you amend your hypothesis accordingly. And once your hypothesis confirms the fact, it can predict beyond that whatever you have discussed. You can always say that this hypothesis now can become a law, or it can become something which is reportable. We then gave you a broad definition of physics, that we said physics is defined as something which deals with measurement. It measures the physical properties of matter, and we also said that physics looks at the interplay of energy and its relationship to matter. And that was the broad definition. And because we've looked at the broad definition, we said because it is dealing with comparison, the physical parameters, therefore we need to have a measurement system. We discussed what a measurement system is, why the scientists, physicists require a measurement system, what are the measurement systems we deal with. We said in physics we are dealing with the System International, which is based on a convention used by different international bodies. It is based in France, and it gives us 7 fundamental units, 2 supplementary units, and quite a lot of derived units. We then discussed how we represent a quantity or something in physics. We said you require 3 different things. You require a magnitude, a number, you require a unit, and if it is a vector or a scalar, you require a direction. We did not discuss what the vectors and scalars were at that point of time. That is what we are going to discuss today. We then discussed what is the use of a prefix, the unit, the scientific notations. This was basically, we had discussed how we are going to depict large numbers and small numbers by use of the scientific system, and we gave you examples why we required to have such a thing of representing very large numbers and of representing very small numbers. For example, the mass of an atom would be 10 to the minus 27 kilograms. In other words, it means that you have 10 to the 27 atoms forming about 1 kilogram of mass. In the other scientific method, when you have very large numbers, for example, if we are looking at the distance from here to the sun, which is 105 million meters, we will represent it as 1.5 and 10 to the 11 meters, which writing in the scientific notations gives us a means of comparisons of different things. We then looked at the interplay of physics with respect to the other 2 branches, why physics is known as the fundamental science, because physics is the fundamental science. It deals with the fundamentals of physical parameters. Biology and chemistry, even though they are sciences, deal with the interplay of physical laws in their system. Then we looked at, in the last lecture, what are the main branches of physics. We said physics historically has been divided into 2 main branches, that is classical physics and that is modern physics. Classical physics encaps mechanics, electricity and magnetisms, waves and vibrations, and of course optics and thermometry. Then we looked at mechanics and its subdivision. We said there are 2 subdivisions of mechanics, basically kinematics and dynamics. Kinematics dealing with the motion of bodies, accelerating motion, initial speeds, final speeds, and so on and so forth, whereas dynamics dealt with the action of forces, and we are going to be dealing with these as we go along. We started lesson 2 with you looking at the states of rest and states of motion. We discussed that there is no such thing as absolute rest because everything with relative to something is moving. For example, we said this table, even though this table is stationary, with respect to me, it is not moving, but this table is part and parcel of this earth. The earth is revolving and earth is moving and rotating as well as revolving around the sun, and therefore it is a state of continuous motion. However, because the laws of physics do not change, if we consider objects with respect to something else, then an object which is moving along this table can move with the same relationship on a table in Australia. Therefore, we can use the same relationships. We stopped at that point, and we are now going to move on into this scheme of work where we are going into the other parameters of mechanics. We are going to discuss today are something which new terms. We are going to be looking at physical quantities. We have said we are dealing with physics. Now, physics basically deals with physical quantities. What exactly are physical quantities? What do we do with them? And how do we go about looking at them? We will right now define what is a physical quantity. We will name some quantities which are physical and why some quantities are not physical. We will give you some examples of physical quantities, and then we will just proceed further with some other things to give you identification, how we differentiate between two specific physical quantities, which we are going to discuss at a later stage. But in this lesson, those two physical quantities are, of course, scalars and vector quantities. Now, when we define a physical quantity is that which can be described, or it can be measured in terms of fundamental, derived, or the supplementary units. For example, if we can measure its length, we can measure its mass, we can measure its temperature, then that quantity is a physical quantity. Let's say you have 1 liter of water. 1 liter of water will remain 1 liter of water, whether I measure it, you measure it, or someone in some other laboratory somewhere else measures it. 1 liter of water will remain 1 liter of water. A bullet traveling at a certain speed, when it leaves the rifle, it will remain the same irrespective who measures it. Therefore, the speed of a bullet is a derived quantity, and therefore it is a physical quantity. An amount of gas which you fill in a cylinder, amount of the gradient of a road, that is the angle, how many feet after how many kilometers is the height you gain. For example, you move from point A to point B, you gain an elevation of 2 meters, then the gradient would be 2 meters per that distance you have traveled. Let's say 2 meters per kilometer or 2 meters per 100 meters would be the gradient. The gradient, of course, is a physical quantity. Now, do remember one thing, that the physical quantities remain same, irrespective whether I measure it, you measure it, or someone else measures it. Now, are there any quantities which are not physical, which cannot be measured? We always say those quantities are not physical, which are dependent upon the observer. Now, let us say there are two people. I present to them a flower. One person will say, "What a beautiful flower." The other will say, "What is this you are showing me? It's just petals and thorns, nothing else, not something to bother about." Now, two people are looking at the same object, but they're having two different opinions. In other words, we say this is a quantity which is dependent upon the observer, therefore it is not a physical quantity. The examples are emotive or static measurements like love, hate, beauty, happiness, stupidity for that matter, etc. These are all non-physical quantities. Now, quite a lot of people do say that these quantities are also essential. For example, aesthetics, beauty, love are very, very essential quantities to measure the relationships of people. It's measure the responses of different mobs, of different classes, and we rely on these for formulating our opinions and formulating our responses. However, because these will depend upon who is making the observation and who is at what time is the response of certain people. For example, I pose a question to my class, I look at the responses of different students. Some students might be very responsive because they have understood what I have said. others would be mildly responsive. They have not very well understood it, or perhaps their attention was elsewhere. Now, the same question which I have posed or same information which I have given is perceived differently by two sets of people. Therefore, I cannot say that this is something which I can say is absolute. In physical quantities, irrespective of who measures it, both will measure within the limits of the measurement system the same similar quantities. That is why these quantities which are not physical, even if they are very important, are not part of physics. Physics does not measure these qualitatively or quantitatively. We do not do qualitative measurements. Normally in physics, what we do is quantitative measurements. We try to break down things into figures which we can quote and which is reproduced irrespective of who makes these measurements. Now, what exactly are physical quantities? What are quantities which we can say are physical? Like I said, any quantity which can be referred to in terms of the fundamental units, the supplementary units, or the derived units like length, area, volume, time. These are all fundamental units, and area, of course, is a derived unit. Therefore, we can say these are fundamental units, and these are physical quantities. For example, the area of this table will remain the same whether I measure it, somebody else, the carpenter, comes and measures it, it will remain the same area. And for example, if I construct a house, the engineer tells me, okay, this is your plot area, this much is going to be the covered area, irrespective whether I measure it, the surveyor measures it, or the people from the building department come and measure it. They're all going to agree that, okay, this much is your plot area, this much is the covered area, and that is what we are going to be looking at. Similarly is the case with other derived unit, which we have not discussed yet, but we can look it up, like strength of materials, electrical parameters, magnetic strength, conductivity, resistance, etc., etc., etc. These are all examples of physical quantities. Now, we are going to be looking at a special class of physical quantities. In other words, physical quantities can be further subdivided into two different components. One which require a direction to identify itself. Another which does not require a direction to identify itself. The physical quantity which requires a direction to be identified is known as a vector. A physical quantity which does not require a direction to be identified is a scalar quantity. Now, a scalar quantity very simply requires a magnitude. It requires a specific unit. Examples are distance. Distance is basically moving from point A to point B. Let's say I move across this table. I have covered a certain distance. But at point A, a student goes to sleep. He sees me in this position. Now I am moving and I'm on the other side of the chair. The student wakes up. What the student has seen is I've moved from this position and moved over to this position. Now, as far as the student is concerned, I have just moved in this position, from this point to this point. This is known as displacement. Displacement means movement in a particular direction. I've moved from this position to the other side of the chair. That is my displacement. That is the difference. Now, because the displacement is in a particular direction, it is given a term which is known as vector. To identify a vector, we need three quantities. We need a magnitude, so many meters. I have moved so many meters. I need a specific unit. Of course, the meters which I said is the specific unit, and I need the direction in which I have moved. In other words, I've moved from point A to point B, and general examples which we are going to be discussing in this lecture are displacement, velocity, acceleration, and later on in the course, we are going to be looking at other terms which are force and momentum. In scalar, we are going to be looking at distance, speed, mass, and time. And later on in this course, we are going to be taking up one other item, which is scalar quantity, which is work. Now, scalar quantities, distance I have said is a scalar quantity. Distance basically फासला है, एक जगह से लेके दूसरी जगह का फासला, उसको हम डिस्टेंस कहते हैं. जैसे मैं कहता हूँ कि जी मुझे दफ्तर आने के लिए 5 किलोमीटर का सफ़र करना पड़ता है. I have to drive 5 kilometers to come to work. Please note, here I am not indicating a direction. Okay? I just say I leave my home and my office is 5 kilometers away. Now, do remember that the roads are not straight. They are not geometrically straight. Therefore, I have to move in a zigzag manner, but my odometer on the car is saying 5 kilometers. Therefore, I say the distance from my home to my office is 5 kilometers. I do not mention direction, and that therefore what I'm saying is I'm telling you the distance I am traveling. For example, I go to the park and I walk 5 kilometers. Now, very rarely you will find a park which is 5 kilometers large. Normally you will find a park which is hardly about 400 meters by 600 meters. There is a jogging track around it, and I do my morning walk there because I'm an exercise fanatic. I do 5 kilometers of walk there, but that is the distance I'm covering because I have left my home, gone to the park, moved around in a circle, and come back. I have not moved in any particular direction. Now, when we look at displacement, that is a vector quantity. Now, in vector quantity, I have to measure, I have to indicate the direction. Therefore, displacement becomes a vector quantity. Now, how do I identify displacement in everyday life? Example, the library is 200 meters in this direction. The office of the principal is 150 meters to the left of the corridor. In other words, I'm identifying to the student or the person in which direction he has to move to go to the object. The post office is 2 kilometers south of this building. In other words, I'm telling that person in which direction to move because I'm adding a direction. Therefore, distance becomes displacement. Displacement is, like I said, I'm standing here. I move to the other side of the table. This movement, of course, was the direction or the distance I had traveled. But when I add a direction, this becomes the displacement. A distance can be equal to but cannot be more than the displacement is something which we are going to be looking at. Now, in real life, how do we find such things? On the slide, which we are going to show you right now, I have difference between a scalar and a vector quantity. I have, let's say, there is a river there, shown there, and there is a bridge which is allowing me to cross. I'm standing at point A, and I have to reach point D. Now, in order to reach point D, I first have to move from A to B to the bridge. From B to C, I have to cross the bridge. From C to D, I have to then reach the point where I want to go, which is across the river, where perhaps my friend is standing. So the distance I have to travel is from A to B, which is 1 kilometer, from B to C, which is another 2 kilometers, C to D is 1 kilometer. The distance I have traveled is basically 4 kilometers, which is AB plus BC plus CD, 1 plus 2 plus 1, which is 4 kilometers distance. However, my displacement is only from A to D. So my displacement will be written as from A towards D, a total distance traveled, a vector quantity, but the displacement is only going to be 2 kilometers. Now, when we have quantities which are scalar as well as vector, the rules of adding or subtracting, or let's say mathematics of their addition and subtraction becomes different. Very simply because we cannot add them just like simple arithmetic. In scalar quantities, the rules are very simple. You add them just like everyday arithmetic. For example, if I have got 5 liters of milk and I have another container which contains 7 liters of milk, how much milk do I have? I have 12 liters of milk. Very simply, 7 plus 5 gives me 12, and that is what is known as addition of scalar quantities. I had 5 liters of milk, and I added to it 7 liters of milk, giving me a total quantity of 12 liters of milk, which was what a scalar quantity is. Similarly, I have to move to let's say I have to go to school, and there is a park in between where I do my morning walk. So I walk 5 kilometers in the park, then I move another 2 kilometers to the school. Total movement which I have done is 5 plus 2, 7 kilometers. But again, please note, I have not indicated a direction. But however, in case of vectors, we have a problem. Because just like the example in which I gave you, I moved across this desk to the other side of the chair because that was the only way I could move. Therefore, the distance I have traveled is across the chair to the other point, whereas the displacement has been from this point to this point. On the slide, you can see that we have a distance basically was from point A to B, from B to C, and from C to D, which is 1 plus 2 plus 1, which is 4 kilometers, whereas the displacement becomes from AD towards D, which is my indication towards this side, and that basically is only 2 kilometers. And in that case, we have a direction indicated. Now, the head-to-tail rule, as it is known for the vector addition, is that if you have three vectors, let's say x, y, and z, now the vectors as they are indicated on the slide can be in any direction. We are not specifying in which direction which vector is. We have just three vectors which we are going to add together. Now, according to the head and tail rule, we move from point A to point B. In other words, we use the vector x first. And then wherever x ends, that's point B, we place the start of vector y, the tail of the vector y, at point B and extend that right up to C, because BC is going to be the vector y. Now, the vector y ends at point C. We start the vector z from a point where the vector y ends, which is from C, and it continues on till the point D, and a resultant vector or the displacement would be AD towards D, and that would be from A to T. Now, just to give you an indication, on the next slide, I am indicating that you can add X, Y, and Z in any order whatsoever. You can have X, Y, Z, you can have Y, Z, X, or you can have Z, X, Y in any order. And like the diagram is showing, you have X, Y, and Z is ending at D, you have Z, X, and Y, which again ends at D, or you have Y, Z, and X, which again ends at D. It does not matter in which order you take the vectors, which vector you take first, which vector you take second. The rules of head-to-tail rule will always give you the same resultant. We have other combinations also, a total number of, because there are three vectors, you can add them together in 6 different ways. I have only shown 3 of you, but if you look at, you take a graph paper and plot the 6 possibilities, that is x, y, z, x, z, y, y, z, x, y, x, z, z, x, y, z, y, x. You have 6 combinations, and you will find that in all of these 6 combinations, when you plot them on a graph paper, they will all give you the same resultant, which is A and D. In head-to-tail rule, the advantage of head-to-tail rule is that it allows you to add 3 vectors or more vectors in case you have more of them, and the resultant would be the same irrespective of which vector you take first. Now, examples of scalars and vectors, like we said, mass is a scalar quantity, a mass of 5 kilograms, no direction is indicated. It does not matter whether 5 kilograms is on the table, 5 kilograms is on the floor, or 5 kilograms perhaps in a shop, it will still remain 5 kilograms. And a time of 25 seconds, a time duration of 25 seconds, it does not have a direction. Yes, here I should clarify that time always moves forward. We do not have a negative time. We do not say we have a direction to time. And somebody might argue that time can have a direction. But for our purposes, we will say time is a scalar quantity. It does not have direction. Examples of vectors are displacement. For example, we can say this object is 270 meters north of me. Then when I say this object is 270 meters north of where I am standing, any person who stands at the position where I am standing, looks north 270 meters away, will find that object. Another example is a force of 25 newtons applied to the west. If that is the west direction, then yes, it is applied to the west. We will know that anybody who stands in this position looks at the direction north, south, east, west, and if the west is in this direction, he will immediately say, okay, this object is in this direction. That is the example of a vector quantity. Now, the question arises, is it always necessary to mention the direction with a physical quantity? Like we have already stated, scalars are quantities which do not need a direction. Now, scalar quantities are like, say, 4 kilograms mass, a mass of 4 kilograms, whether it's on the table, it's on the floor, or in a shop somewhere, it will always be 4 kilograms. We do not mention a direction, which direction it is pointing in. Of 4 kilograms of wheat, for example, will remain 4 kilograms of wheat. It does not have a direction. It's a scalar quantity. 11 liters of milk, that's again another scalar quantity. It does not require a direction. However, whenever we have vectors, vectors are physical quantities which are not complete unless a direction is specified. Let us say 300 newtons force acting upwards. It is going to be different from a 300 force newton which is acting downwards. So these are two forces in opposite directions. One is acting upwards, one is acting downwards, and therefore they are two different quantities. Therefore, force being a vector would require a direction. Displacement being a vector would require a direction. Now, please note here, there are certain quantities which are already defined as vectors, like velocity, acceleration, weight. As we go along into this discussion, we'll find these already are identified as being vectors. Because they're identified as vectors, whenever you are solving a problem, in the solution, unless the direction changes, you do not need to mention it. So if, let's say, an object, we say, was at rest, moving to the left, and we have to find its velocity or its acceleration in a certain period of time, we will not in the problem indicate that it was moving in this direction or the opposite direction unless the direction changes. Therefore, physical quantities like acceleration, force, and velocity, which we already have identified as vectors and are in normal use, are known to be vectors, do not have to have a direction identified unless in the solution of the problem, the direction has to change. Now, what we're going to do in the next few portion of this lesson is look at examples of vectors and scalar quantities. We are going to be looking at examples of distance and displacement, speed and velocity, acceleration and deceleration, identify which are vectors and which are scalars, and move on as we go along. Now, like we said, displacement is amount of movement in a particular direction. An object moves from A to B in direction A to B. It is a vector. Distance, I move from this point, move around the table, go to the other end of the chair. Like I said, again, I have moved a distance of 4 or 5 meters. I do not indicate direction. Therefore, it is a scalar quantity. Therefore, displacement becomes a vector quantity. Distance becomes a scalar quantity. Very simply, when I'm saying distance, I am not indicating a direction in which direction we are moving. Now, whenever we say the movement, distance, and displacement, what are the unit of distance and displacement? In both cases, the unit is the meter. The meter is identified as the unit of length. Distance being length has to have a unit of meters, and displacement, again being length, will have a unit of a meter. The unit of meter which normally we use in the SI system is a meter. Its symbol is M. There are units in common use which are smaller than the meter. There are units in common use which are larger than the meter. The units which are smaller than the meter, which are in use in physics normally, are a centimeter, which is 1/100th of a meter. Normally, this is about a meter rule. A centimeter is a very small quantity. It is about 1/100th of a meter. In 1 meter, you have 100 centimeters. Another unit which you use in normal everyday life is a millimeter. Every centimeter has got 10 millimeters. A millimeter becomes 1/1000th of a meter, or 1000 millimeters make 1 meter. In physics, we also use a micrometer, a nanometer. These are units which are smaller than a meter. When we move to units which are larger than a meter in our common language, we use kilometers, which are in everyday life. We say distance of a kilometers. Kilo means 1000. Unit of 1000 meter is a 1 kilometer. A megameter is a unit which is rarely used. It is 1 million meters, and it is a rare unit. Sometimes you do find it in literature, megameter, capital M with a small m. Then larger units, of course, you have astronomical unit. An astronomical unit is the distance from the Earth to the Sun. We take the average distance, and it is available in astronomy and physics books. It is 1.5 in 10 to the 11 meters, and it is 150,000 million meters is the distance from the Earth to the Sun. That is known as an astronomical unit. An astronomical unit is a unit which is larger than a meter. Another unit which is common in astronomy is a light year. A light year is 9.4 into 10 to the 21 meters. It is 9, 4, and 20 zeros. It's a very large number. It is in common use in astronomy because when you are looking at the stars, the distances from our sun to neighboring stars and furthermore to other stars are very, very enormous. For example, the nearest star which we have to our solar system is about 4 light years away. That means it will take light 4 years to reach from our sun to that sun. And that is something which is a very large number. It will be about 4 into 10 to the 22 meters, something which normally would become incomprehensible if you are already going into scientific notations. So astronomers use a unit which is light year, which is unit larger than a meter. When we look at speed and velocity, this is again two quantities. One quantity is a scalar quantity, the other quantity is a vector quantity. Like we discussed earlier when we looked at rest and motion, we said speed is defined as the distance moved divided by time taken, and velocity, of course, would be displacement or distance moved in a particular direction over the time taken. In both cases, the unit is again going to be the same. It is meters per second, kilometers per hour, or in other words, distance moved divided by time taken, or displacement divided by time taken. And like we discussed, displacement and distance both have units which are meters. And therefore, time has units which are seconds, with speed and velocity automatically have same units, which is meters per second is the SI unit, but you can have derived units which are kilometers per hour or perhaps non-SI units like miles per hour. We do not normally indicate direction in speed and velocity because their names differentiate that this is a vector quantity, then this is a scalar quantity, speed being a scalar quantity, velocity being a vector quantity. And we do not normally indicate the direction unless when you're solving the problem, the direction changes. The SI unit per speed, of course, is meters per second. The symbol, normally you say meter per second, meter slash second, or meter second inverse. Other units which we are normally using is centimeters per second, for example, 2.54 centimeters per second. People who have used tape recorders, this is the speed at which the tape moves along the tape head. 2.54 centimeters per second is the standard speed for a tape to move across cassette tapes, not the spool tapes. Kilometers per hour is another unit which is unit of speed and velocity because it is an everyday unit, and it can be converted into SI unit because it is again distance divided by time. Now, when we are looking at velocities, there are different types of velocities. Don't be afraid of it. It does not mean that there are different velocities we are looking at. There is only one thing, a velocity is displacement divided by time. However, for solution of problems, we have divided velocities into different types. We say there's an initial velocity. Initial velocity is that velocity which is at the start of the problem. Wherever you say our coordinate system or problem time 0 starts at this point, then whatever the speed or the velocity at that point is, because we are dealing with the velocity in a particular direction, therefore speed in a particular direction, therefore we say velocity at that time is known as initial velocity, and we rewrite it as v subscript I, like I've shown on the slide. The final velocity at the end of the problem or at the end of the question which we are asking, let's say after what is the speed after 5 seconds. Then after 5 seconds, we say that is the final velocity, and it is denoted by a symbol VF. Average velocity is basically the average velocity over that period of time, over that period of movement, and it is known as V average. However, the general symbol which we use for all velocities, like instantaneous velocity, constant velocity, or variable velocity, is V. All velocities, because of the original definition, displacement over time, have a unit of meters per second. And of course, the derived units, we can always put them there, that is centimeters per second or kilometers per hour. They're all basically, the velocities have the same unit. Now, on this slide, I have given you the definition or the formula for finding the average or the instantaneous velocities. The average velocity is total displacement divided by total time, and the symbols for that are S divided by T. Or we can say the average velocity is the starting velocity plus the final velocity divided by 2. That is what we use in ordinary arithmetic. Let us say I start this day with 10 rupees working in a shop. At the end of the day, I have 100 rupees in my pocket. So what's the average money I had over the whole day? So I would say 100 plus 10 gives me 110 divided by 2, 55. So I have over the average over the whole day, 55 rupees per, that is the average amount of money I had throughout the whole day. Or the average amount of energy which I'm spending over the whole day, similarly can be counted out. Averages normally are the two quantities divided by 2. So in case of velocity, is its initial velocity plus the final velocity divided by 2. Now, instantaneous velocity. Instantaneous velocity is basically the velocity at a particular instant. Now, because mathematics does not allow us to divide anything by 0, we say the time period which we are taking is a very, very small instant, but not 0. So V instant is the limiting velocity at that point of time. And it is defined as S divided by the change in time over that very small period. We will not go into the mathematics of limiting velocity because that is beyond the scope of this course. But I have given you the relationship in case somebody wants to look into it, or we can always discuss it when we go into the relationships with you during the assignment periods. The other definition which we're going to be looking at is the relative velocity. Now, relative velocity is always a velocity when there are two or more bodies which are moving with respect to each other. And relative velocities basically have two relationships. Either the relative velocity is the difference between the two velocities. If the objects are moving in the same direction, I have one car, the other car is catching it, and therefore the difference between the two velocities is going to be the relative velocity. In this case, if they are moving in the same direction, it is V2 minus V1. And if the cars were moving in opposite directions, then the relative velocity would be V2 plus V1. And the example, of course, which we have in everyday life is cars which are moving along the road. Now, we have looked at average velocity. Now, we know we had initial velocity and we had final velocity. This is velocity which is changing. Now, because if the velocity is changing, then we define a new quantity, acceleration. Now, acceleration is change in velocity divided by time taken. We have already stated that velocity is a vector quantity. Now, if you are dividing a vector quantity by a scalar quantity, which is time we have already stated is a scalar quantity, the resultant, of course, is a vector. That is why acceleration is a vector. It has to have a direction, and acceleration is change in velocity divided by time. That is the final velocity minus the initial velocity divided by time taken. So if the velocity changes from 10 centimeters per second to 20 centimeters per second, then the change in velocity was 20 minus 10, which is 10 centimeters per second, and the SI unit therefore becomes centimeters or meters per second squared. Meters per second is the unit of velocity divided by 1 second again, and therefore it becomes meters per second squared is the change in velocity. And just like velocity, instantaneous acceleration is going to be the limiting value of change in velocity over a very small change in time. We again, like I initially said, because we are not allowed mathematically to divide by 0. Therefore, we take the instantaneous time, a very, very small interval of time, and it gives us the instantaneous acceleration, and which we will solve in different problems. Again, these problems is beyond the scope of this particular lesson, but I have indicated the formula there, and you can always look it up, and we can also discuss it in the assignments and when we have an interaction with you. Now, we have said there are two quantities, acceleration and deceleration, in the list of new terms which we were going to discuss. In this, we stated there are the two terms which are acceleration and deceleration. Now, there is a similarity and there are some differences. Similarity, both are vector quantities and both have the same SI units, which is meters per second squared. The difference is acceleration is increase in velocity. A car starting from rest, speeding up, is having an acceleration. A car is starting from rest at a green light. You see a green light, you press the accelerator, and the car accelerates. In other words, its speed is increasing. We say it is accelerating. Whereas deceleration is a decrease in velocity. The final velocity is always less than the initial velocity. In other words, there was a car moving, it sees the red light, applies the brake, and stops. Therefore, the speed is decreasing, and a decreasing velocity would always indicate a deceleration. Now, deceleration and acceleration, sometimes you say a negative acceleration is deceleration, the negative sign indicating a direction. Let's pose a few questions. We have to differentiate between distance and displacement, differentiate between speed and velocity, differentiate between acceleration and deceleration. We've already done these, but we are going to revise them and look at these differences. Another question which we are going to be looking at is let's say we are looking at a problem, and we are going to be doing that as we go along. Now, let us differentiate between distance and displacement. Very simply stated, distance is a scalar quantity, where displacement is a vector quantity. In other words, length between 2 points is distance, where displacement is the length in a particular direction. The example I gave you is the distance was moving around this table to reach the other side of the chair, where displacement is from this position to the other side of the chair. Now, another example in everyday life is, let's say, along the motorway. A distance from Lahore to Islamabad is 380 plus kilometers. Whereas if you look on a map and you measure on the map, Islamabad has a displacement of 230 kilometers northwest of Lahore. Now, displacement means in one particular direction. You place a foot ruler from Lahore to Islamabad, measure the distance, and look at across the scale of the map, and you are going to find the displacement in a particular direction. Now, do remember, along the motorway, you have to cross rivers, you have to pass through mountainous terrains, you have to turn left, you have to turn right, and therefore the distance is more than the displacement. Speed and velocity. Speed is distance covered in a particular time, and velocity is speed in a particular direction. The former being a scalar, the latter a vector quantity. Now, in the earlier example, when we said that the distance from Lahore to Islamabad was 380 kilometers, and if it took 4 hours to reach there, then I was traveling at 95 kilometers per hour, which would be the speed. But however, if we look at the displacement, I said displacement was 230 kilometers, and it again takes me 4 hours to reach there, then my velocity would be 57.5 kilometers per hour in the northwest direction. Acceleration, of course, is increase in velocity, and deceleration is decrease in velocity, and in this case, both are quantities. Now, let us look at an example. We have a small bob, which is whirled in a circle at a constant speed of 5 meters per second. Now, the question which we are raising is the velocity of the ball a constant? Now, we already have stated speed is constant. A small bob attached to a string, moving in a circle at a constant speed of 5 meters per second. Because speed is constant as stated, the bob covers equal distances in equal time, and therefore it is moving at a constant speed. However, When I'm moving this bob around, when it was here, it is moving in this direction. But when the bob comes here, it is moving in a different direction. Because the two directions are different, therefore, I say the velocity is changing because direction is changing. Do remember, velocity has got two components, the magnitude and the direction. Because speed is constant, magnitude does not change. However, direction is changing, hence velocity is changing. And like we know, acceleration is the acceleration of the ball constant? Because acceleration was defined as change of velocity over time, because velocity is changing, acceleration has to change. And because this magnitude of the velocity is constant, therefore the magnitude of the acceleration also has to be a constant. And it has to be pointing at a different direction depending upon where the bob is. If the bob was this, over here, acceleration would be inwards. If the bob moves in front of it, acceleration would be towards me. In other words, the acceleration is changing even though the magnitude of the acceleration is a constant. Now, what would be the acceleration of a body which is moving at a constant velocity? There is an object which is moving at a constant velocity. What would be its acceleration? Now, if the velocity is constant, then A, the direction is not changing. B, the magnitude is not changing. Both the components of the velocity are not changing. And because both components are not changing, therefore, acceleration being defined, change of velocity divided by time, change of velocity is 0, then the acceleration, of course, is 0. There has to be 0 acceleration whenever an object is moving with a constant velocity. Hopefully, we look at it, and let us look at a numerical. Let's solve a numerical, because solving a problem is the best way to understand what a physicist does or how physics works at understanding what the scheme of work is. A runner is running on a track which is 400 meters long. It takes 42.8 seconds time to run around the track. I have taken these figures from a university calendar, and therefore this is a normal speed which a runner runs at 400 meters. Not, of course, the world record, but of course this is what a student would normally run when at a university level. Now, the data which we have are two things which we know. We know the distance covered, which is 400 meters. We know the time taken, which is 42.8 seconds. Information required, which is the average speed. Do we have a relationship for such an average speed? Yes, we do have a relationship. Speed is defined as distance divided by time, or S divided T. The distance which we have is 400 meters. The time, which is 42.8. And if we divide 400 by 42.8, we get 9.35. And therefore, we can conclude that the speed is 9.35 meters per second. I am giving you two other numericals, which basically I'm just stating them, and we will be discussing them in the next lecture, where I'm giving you time to look at these, do them on your own, and then the next lesson we are going to go into detail and we are going to solve these numericals. The first numerical is stated is car starts from rest, accelerates in a straight line at an acceleration of 3 meters per second square. What would be its final velocity after 30 seconds? That is the question, which is numerical for you to solve. Another numerical which I'm giving to you is that on a highway there are two vehicles, two cars moving on a vehicle. One is moving at 18 meters per second, the other is moving at 22 meters per second respectively. Find their relative velocities if A, they are moving in the same direction, and B, they are moving in the opposite direction. Let me explain it again. We have two objects which are moving in the same direction and in opposite direction. Speed of one is 18 meters per second. The speed of the other is 22 meters per second. We have to find out, when they're moving in the same direction, how fast they are approaching or separating from each other, and when they are moving in the opposite direction, how fast or how slow they are moving or they are separating from each other. Now, in this lesson, what we have done is we have looked at physical quantities, Physical quantities I defined as only those quantities which we can measure in terms of the fundamental units, the fundamental quantities, the derived quantities, or the supplementary units, or anything which has got fundamental, derived, and supplementary units, and we can measure it and compare it, is a physical quantity. Do remember, whenever we measure a physical quantity, irrespective of who measures it, the measurement has to be the same, within limits of error, of course, that I might measure it as 12.21 meters, and someone else might measure it 12.22 meters, because within the limit of the measurement system, there might be a small error. Non-physical quantities were those which different observers will measure differently. Like I say, I might find a poem very beautiful, very enchanting, whereas another person might say that I really don't understand what is this poem, what is it about. Now, perceptions or emotions of two persons are different. Therefore, we say this is a non-physical quantity. We looked further divisions of physical quantities. We looked at the two basic subdivisions, that is vectors. Physical quantities which have directions are known as vectors, and physical quantities which do not require a direction to be identified are scalars. Examples were mass, examples were time. In case of vectors, it's velocity and acceleration. We then gave you specific examples of different vectors and scalars, like distance and displacement, distance being a scalar quantity, displacement being a vector quantity, speed and velocity. The speed was a scalar quantity and velocity was a vector quantity. And of course, we looked at acceleration and deceleration. Both of these were vector quantities. And that is all for today. We will meet again in the next lesson. Thank you very much.